chapter 13, chi-square test. So this is when we are dealing with binomial distributions or count data. Right? So it's categorical data. And if we have, you would recall the binomial distribution is used to analyze experiments or trials that have two possible outcomes. How many did this with econometrics 2222? The binomial distribution, do you recall that? Good, right, two outcomes. It could be pass or fail or success or fail or yes or no, any two outcomes. An extension of this is what if you have more than two outcomes? What if we have more than two outcomes, we call it a multinomial distribution. Right, so more than two outcomes can occur. And so when we have that, we have what is called, we can run a test called the chi-square goodness of fit test. It's used to analyze probabilities of a multi-nominal distribution trials along a single dimension. So that's test one. And it compares expected theoretical frequencies of categories from the population distribution to the observed. So that's the actual. So what we would expect, and we compare that to what we actually observed once we collected the data. Then we run this chi-square test to see if it's the same or not. So we go with, well, are the distributions the same? And the alternative hypothesis is the distributions are different. So I give an example. This is test one. There's going to be a second test that's in part the second section of this short chapter. It's called the chi-square test of independence. So they're both chi-square. Chi-square distribution has a lot of a whole family of tests, and we're looking at two. We're looking at the goodness of fit test to see if the distributions are the same, and we're also going to look at the test of independence. When we have two different variables, we just test to see if they are independent or not. Right. So when the expected value of a category is small, a large chi-square value can be obtained erroneously, leading to a type 1 error. These are things to think about. Control, we just make sure when we do these tests, we want to make sure we have the condition that it should not be used if any of the expected frequencies are less than 5. If they're 5 and more, you're good to go and do this test. If they're less than 5, then you shouldn't do this test at all. Okay? And if you look at the test book exercises to prepare you, this is what the coverage for the lab and the next quiz is. So you can look at these. There's just a small set of questions for chapter 13, but you'll see some questions. Are we safe to proceed with this chi-square test? You just look at the expected frequencies that you calculated and go, they're 5 or more, we're good. Each one of them. And you might be going, well, I don't know what expected frequencies are. We will look at what they are right here. So this is the formula that we use to compute the test statistic. It's a chi-square test statistic. And we just sum each of the frequencies. So Fi is the frequency, and this is the same notation as the textbook not to confuse anyone. So the Fi, you'll hear me call it the observed. I'm just so used to saying the observed, subtract the expected, divide by the expected. I just know that off by heart. So the observed frequency, subtract the expected, all squared in the numerator, divide by the expected. So it's a really straightforward formula to remember. And the degrees of freedom is the number of categories, K, subtract 1. And we'll look at an example. So it's pretty short. We're going to have a short lecture today because there's only 2 examples in this chapter, and then we'll do a short intro to the linear regression. Okay, so the goodness of fit tests. 1, compute the expected counts given a sample size and the probability. I'll show you how we do that, specified by the null hypothesis. 2, step 2, we calculate the chi-square test statistic, its degrees of freedom, and we get the critical value. So there's going to be the chi-square test, and we're going to compare it to the chi-square star. critical value from the chi-square table of theoretical values. I call them theoretical because they're made up of the perfect distributions dependent on the degrees of freedom. Whereas the chi-square test value, that's just the test statistic, it is random because it's coming from the data. We just compare them and we interpret the results. And if the chi-square test statistic, you guys can probably guess this. If the chi-square test statistic is greater than the critical chi-square value, what do you think we're going to do? We're going to reject the null hypothesis. It's the same decision rule, right? So it's very consistent. You'll start seeing a lot of patterns in this, and our conclusions are very consistent. So let's try an example. I think the best way to understand this goodness of fit test is to do an example. So if we look at absenteeism from a university, we have what we would expect, or what the faculty perception is. And we have 100 students. 100 students, if you just think of this distribution, 50 plus 30 plus 12 plus 8 come to 100, right? 100 students. And so we can get the probabilities of this as well. Or the proportions. So P1 would be, and we assume these as being theoretical because this is expected. So we don't put a hat on these P's. We expect that this is the faculty perception. And this is what they believe that the absenteeism is. So if for 0 to 2 days, 50% of the students will be absent. 3 to 5 days missed. They expect 30% of the students to be absent, right? So 30% of the students will miss 3 to 5 days, 50% of the students will miss 0 to 2 days, and 12% of the students will miss 6 to 8 days, and finally, 8% of the students will miss 9 or more days. That's the faculty. This is what they base it on, based on their history and their knowledge, right? What they think it is. So this is what the faculty expects for every 100 students. Okay. Data is then collected. This is the actual. And we're going to go, okay, what happened here? The observed data then is collected by the faculty. They take attendance and they find that 0 to 2 days, it's 35%, right? 40% missed 3 to 5 days, right? 40% of the students missed 3 to 5 days. 20% of the students missed 6 to 8 days, and 5% of the students missed 9 or more for every 100 students. So we can run a test to see if what they expected was the same as what actually happened. And that's called the goodness of fit test. So we just add those up. Well, let me just grab this. So the null hypothesis is basically the collection of those proportions that they expected. What was this was 12%? This was, so we have 4 groups, right? K equals 4 in this grade, right? Because we have 4 groups, we have 0 to 2, right? This is group 1, this is group 2, group 3, group 4. So group 1 is 0 to 2 days, group 2 is 3 to 5, group 3 is 6 to 8 days, and group 4 is 9 or more days against. So that's what we hypothesize, that's what the faculty expects. We against the proportions are not the same. as the faculty perceptions. So basically we're saying that the distributions the same? It's really what that's all saying. Are the two distributions the same? What it was expected compared to what was observed, what actually happened. We're going to just compare the two, and we will do that right here. So group 1. So 0 to 2 days absent. I'm going to give myself lots of room here. It's going to be f of I subtract e of I squared divided by e of I. And that contribution for group 1 is 35. Subtract 50. Divide by 50. Because the frequency that was observed was 35 students. But what they expected 50% of the students, 50 students, right? Divide by 50. So the contribution for that 0 to 2 days is 4.5. The contribution to the chi-square. Then we do the next group, 3 to 5 days absent. And we're going to have f of I subtract this. Always write down your formula. Keeps it straight. And this is going to be 40. Subtract 30. Squared, divide by 30. And that's going to be 3.1234. I'm going to carry 4 because I know this is an intermediate step. And it's going to go into the next. Ooh. So you can see where we got the 40 and the 30. It was observed. So we took 35 and subtracted 50 squared and divide by 50. Then we took 40, subtract 30, because that's what we expected, divide by 30. Now we're going to take 20 and subtract 12 squared and divide by 12. That's for the 6 to 8 days absent. So it's still the same formula. 20 subtract 12 squared, divide by 12, and that's going to be 5. I'm going to carry 4 decimals again, and then 9 plus days. And it's going to be, what was it? It's 5 subtract. So they only had 5 students miss more than 5 days, but they expected 8 or 8%. So it's going to be 5 subtract 8 squared, divide by 8. So the contribution for group 4 is 1.125. What do we do to get the chi-square test? Just add those up. 4.5. It's the sum of all those contributions. And see if you get 14.292. We do have a clicker question coming up too. It's on the last slide. So we do have a test statistic. We now need to get that critical value. We need to get the critical value on k minus 1 degrees of freedom, which would be 3 degrees of freedom. And we're going to use alpha, of course. What's our alpha? It's going to be 5%. That's our usual. Right, so I'm gonna just does everybody have 14.292? I'm seeing some agreement. Just verify this is what you get. Right? Yep. Okay, we're gonna go to the chi-square table. You remember the chi-square table from Econ 2222? Looks familiar? We use this one here and we're gonna look at this column, right? Alpha 0.05 on 4 degrees of freedom, 3 degrees of freedom, because there was 4 groups. K is the number of groups, so K minus 1 is equal to 4 minus 1, which is 3 degrees of freedom. And we're going to get 7. We're going to get 7.8147. Right, that's how we do it. Look at the alpha 0.05 column and just get the critical value, the chi-square. We go over here and we get that critical value. It was pretty large, 7.8147. So the faculty perceptions versus what actually happened, what the students actually did, right? We're looking at the actual data. So what they expected to see in absenteeism versus what they observed from when they calculated the actual, what do we conclude? Is there a difference? Yes, there is. There is. So we just go, since the chi-square test is greater than the chi-square critical value, we reject. And we conclude there is a difference. And I'm going to say it this way, there's a difference, a statistical difference between the two distributions. Right? The faculty perception versus the observed distribution. Okay, how's that? We're good. That's the only example I have for the goodness of fit, but there's several more in the textbook, which is as a 2-hour loan, right? At the library, and there's lots of questions to try, a few questions at least. So the second one from the chi-square family is, are we okay on this? We're good. So what they expected to happen was different than what actually happened. Right, so we're going to look at the test of independence. This is the second test for this chapter, and I have one example with a clicker question following. So we're going to look at, these are used to analyze the frequencies of 2 categorical variables with multiple categories to determine whether the 2 variables are independent from each other. So the null hypothesis is the 2 are independent versus the 2 are not independent. And if they're not independent, then they are dependent. Meaning knowing one can tell you information about the other. Right, so the example I use, it's an accounting example. There's quite a few of you in accounting. So I have an accounting example. This is the formula though, I guess we should look at the formula. The chi-square test statistic is because it's in a 2-way table, it's in a contingency table. It's like a pivot table, right? Contingency table. So you have your observed again, right here, observed. Minus E for expected. E, that's why they're E's, by the way. I think you already came to that conclusion. So the observed frequency, subtract the expected, that's the capital E, divide by E. With degrees of freedom, because we have a 2-way table here, the degrees of freedom will be R is the number of rows, R for rows, and C is the number of columns. So R minus 1 multiplied by C minus 1 is the degrees of freedom. And you get the expected counts by taking the row total. That's the row total multiplied by the column total for each tabulation in the table. So whatever tabulation you're looking at, it will be that row total multiplied by that column total, divide by n, which is it's the overall total, the grand total. So the grand total, remember the two-way tables? You could get a grand total in the bottom right. And that's your chi-square test. The null hypothesis is the two variables are independent versus they're not independent. If the chi-square test statistic is greater than our critical value on r minus 1 times c minus 1 degrees of freedom, we reject the null hypothesis and conclude that the two variables are non-independent, meaning they're dependent. Are we ready to go? We can start the next one here. So the two variables are independent. That's our null hypothesis versus they are not independent. So we're going to run this test using this accounting data. So you probably know more about these depreciation methods than me, better than me. So there's 3 different depreciation methods. There's a straight line, we denote with S, declining balance, we denote with a D, or using a combination of the two. We have different countries, right? We have countries. So R in this case equals 1, 2, 3 depreciation methods. C in this case equals France, Germany, UK is 3. So the number of rows is 3, the number of columns is 3. You can see I have the totals on there. It's coming from an example from the textbook. The totals are already on there. The totals of, right? The totals for each row, 43, 35. The totals for each column are the same, they're 26. And we can calculate all of the expected values. So we're going to use alpha equals 5% again. And our degrees of freedom will be 3 minus 1 times 3 minus 1, which is 2 times 2, which is going to be 4. Okay. 4. And our expected count is each one of these times this divided by n. N is 6. This is our n. 78. So if I'm going to put in brackets. I'm going to put in round brackets beside the raw counts, the expected counts. So for 15, we would take 40 times 26 divide by 78. So here's an example. So we would take, for 15, we would take 40 times 26 divide by 78. This is for 15, that cell right here for France and straight line. And we would get out of that 13 and a third. I'm going to keep it in fractions just to save space. And so in round brackets, we expected 13 and a third, but the observed was 50. For 0, we do the same thing, the same number. They got 0, so we expected 13 and a third, but they got 0. That's what was actually collected in the data. For the UK, same thing. They expected 13 and a third, and they got 25. Using the margin, right? We're using the margin. So if we do the same thing for 1, we would take 3, that's the total for that row, the declining balance, right? So for 1, they expected 3 times 26 divided by 75, which comes to 1. They expected 1. They expected 1 and they expected 1. So there's a lot of equality going there. 1, 1, 1. They expected 1 and they got 1. Same thing with the last group there, the tabulation is 10. We'll do 10. So that's the combination of the declining balance and the straight line. So that row total is 35 multiplied by the column totals 26 divide by 78. And it's going to be 11 2/3. Or another way to say it is 11.6666 or 6667. I'm just putting 2/3 to save space because it's going to be hard to get all the sixes in. And the same for the next one. So that would be 35 multiplied by 26 divided by 78. We get the same 11 2/3. And they got 25. And the last one, they expected 0, but they expected 11 2/3, but they got 0. The ones in the brackets are the expected. The expected are in the brackets using that formula. So now we can just, by row, we're going to spin out the chi-square test statistic. So it's going to be, remember, it's always the observed frequency, subtract the expected, squared, divide by the expected. It's the same formula as we did before. So it's just going to be observed is 50, subtract 13 1/3. When you put it in the calculator, you would go 13.3333, something like that. Just get the thirds in the decimal places. I'm just saving space. So that's for the 15. The next one is going to be 0, but they expected 13 1/3 squared. Divide by 13 1/3. And the next one is they expected, or they got 25, but they expected 13 1/3. Divide by 13 1/3. The next row, and we just add all these up. So, but the question said, what's the contribution to the chi-square test with straight line and France? You would just calculate 15 subtract 13 1/3 squared, divide by 13 1/3. That's just that tabulation. Right, that's just that one contribution. Right. But here I'm doing for everyone. So this is going to be just, these are all going to go to 0. We can almost wipe out this row. We don't even need to calculate it because they're all going to 0. And the last one is 10, subtract 11 2/3 squared, divide by 11 2/3. That's the contribution for the combination DNS and France. Then DNS and Germany would be 25. And they expected 2/3. And finally, the last one is 0. They got 0, but they expected 11 2/3 for the UK. Contribution would be that value there. But if we add up all of these contributions, actually, I'm going to do it right here, equals, drum roll, 50893. You can definitely verify this. So for the 13s and the thirds, you can go 13.3333. For the 11 2/3, just do 11.6666. And you can go through and add them up. You don't need to add up the middle ones because these are all going to 0. 0, 0, 0. Those are all 1 subtract 1 and 0. So those are going to be all 0. You just need to add 6 quotients and you get hopefully 50.893. We then look at our critical value. Right, our critical value for chi-square, right there, is the table value on 4 degrees of freedom. 4. And we're using alpha of 0.05. So I'm going to change screens to get that table value. It's going to be 4 degrees of freedom, so just below the one we just did for the goodness of fit test. And I get 9.4877. We're good? Everybody agree with that? Okay. We go back. So what we're testing is, are the countries and the depreciation methods independent of each other? In other words, they're not related. Or are they related? So based on our data analytics skills,